Hi everyone, welcome back to Geeks for Geeks practice and welcome back to the Microsoft in 29 days self-paced course. So just a quick reminder, in case if you have not registered for the Microsoft in 29 days self-paced course, so you can find the link of this course in the description of this video. It is completely free of cost, and once you register for this course and click on the start button, then you can find that you will get access to all the 29 days that are there. You can see you'll get access to each and every day, and here you can see that on a particular day, as I have told you that I have already solved on every day, I have solved two problems as classwork. So you'll get the two individual recordings of the problems. You will also get this on YouTube, and apart from this you will also get the problems. So you'll get two problems to submit that I have solved already, and you also get other three problems on the same topic as homework. So that is 5 problems per day, which makes it a total of almost 30 into 5, that is 150 problems. So you'll solve 150 good problems in this course, and apart from this you will also be able to track your progress among the other people through the help of leaderboard. So make sure to register for this course if you haven't already, because it is free of cost and you might be missing out a lot of good things. So make sure to register in case if you haven't. Let us discuss the problem, that is word wrap. The problem says that we have been given an array nums which denotes the size of every ith word. So it denotes the size of every word. Nums of I denotes the size of every ith word. Okay, let k be the limit. So what is this limit k? K denotes nothing but the number of characters that I can have in one line. Okay, so what I have to do is I have to put line breaks in given sequence as that lines are printed cleanly. Okay, so assume that the length of each word is smaller than the line of the word. Okay, so every word is smaller than the number of characters that I can put in a particular line. Okay, when line breaks are inserted, there is a possibility that extra spaces are left in each line, and we need to count them as cost. So we need to minimize the cost and we need to return what is the minimum cost. So let's consider the sample example that has been given. So suppose the sample example here that has been given is 3, then we have been given 2, then we have been given 2, and then we have been given 5. Okay, so if this array has been given, so the first index denotes the first element, the second index denotes the length of the second element, the third index denotes the length of the third word, and the fourth index denotes the length of the fourth word, right? So every index of the array denotes the length of the word one by one. Okay, we are not actually given the words, we are just given the length of the words, and we are given here k value suppose as 6. If we are given k as 6, so that means there are 6 characters that I can put in one line. At most 6 characters I can put in one line. If suppose the word is of if suppose the word is of length 3, so suppose I say that the word of length 3 suppose is gfg, right? So I'll write them one by one. Suppose the word with the length 3 was gfg. Okay, I'm assuming it, although it was not given. Suppose the length of word 2 was, let's say, something like go, which is programming language. Suppose the length with length with word 2 was 2, like cp. Then suppose that the length with like the word with length 5, let's say, was coder. Okay, these are the words that I had here. So what I can basically assume here is, like, if I have been given a particular word, like let's say I'm at a current line. Okay, suppose I have 6 spaces in front of me. Suppose I have 1 2 let's say I have spaces, let's say 1 space, 2 space, 3 space, 4 space, 5 space, 6 space, right? So initially I have gfg, so suppose gfg I have put. Okay, then I move to the next word. Suppose I move to the next word which is of length 2. Suppose this word is go. Notice that you have to put you have to get the words in terms of the order that they are given. Okay, you cannot change the order of the words. Basically you cannot change the order in which you place words one by one, although this is imaginary, but this length of the words is true. Okay, now what we can do here is, suppose you have to put the word go. Okay, so obviously one more thing that you have to observe is, if I have to put go, so I'll not put go like this, because if I have to write the words, right? So if I write go like just after gfg, so I'll not be able to differentiate or distinguish between gfg and go. So what I will be doing here is, I'll always take one space after a particular word is over. Okay, I'll take one space, so I'll not put anything on this place. Okay, and then if I want, so I have a choice, right? Either I can put go here, or suppose what I could have done is, I could have put go in the next line as well. Okay, suppose I had put it in the next line. Okay, so suppose I had the choice and I had put the word go in the next line. In that case, you can see that I am having some spaces. Okay, I'm having some spaces. Now when I had put the word go, like suppose I was about to put the word go, right? When I was about to put the word go, then the number of remaining spaces that I was left was word 2. Okay, now if I like remaining spaces were 2. Now either I could have done what? Either I could have placed go in the same line. If I would have placed go in the same line, then I would have not paid any extra cost, right? But if I put go in the same line, if I put go in the same line, then I'll be in trouble. Like if I put go in the next line, in that case, what will happen? In that case, I can say that 3 spaces are remaining. Actually, you will say that no, 2 spaces are remaining, but actually you can see that the number of empty spaces after the last word is over is nothing but 3. So in that case, this will be 3, right? This part will be 3. That is nothing but remaining plus 1 into remaining plus 1. You can observe, okay, because the remaining number of places where I could put characters were 2, but you can see 1 space also I was giving, so that's why remaining was indicating 2. But actually, if I'm not putting a word and all these spaces go waste, so it will be remaining plus 1 into remaining plus 1. So here you can see that it will be 3 into 3, because the cost will be the remaining plus the remaining number of spaces into the remaining number of spaces, that is nothing but 3 plus 3 into that is 9. Okay, after that, let's say I take one more space because I have to put the next word, let's say CP, right? So if either I have a choice to put CP in the same line or not. So if I put suppose CP in the same line, so I'll put CP here. The moment I put CP in the same line, so I have one remaining space, right? I have one remaining space. Now if I see here, so I cannot put a word here. Why? Because what will happen here is, can I put another word here? No. Because can I put coder word here? No, because I'll actually be taking as one space, and when I take as one space, then I'll simply move to the next line. Okay, so now since I'm moving to the next line, so in this case also one more extra space is left. So I'll say 1 into 1 is the cost, that is nothing but 1. After that, if I have the word coder, so coder is the last word that I have, so I'll put coder, CODER. And after that, you will say that I also have one space here as well. No, I do not have. I'll not consider the word after the last space, because if we'll read the problem statement carefully, so it says that the extra spaces include the spaces put at the end of every line except the last word. Okay, so except the last word, every space that is there we have to consider. So here we will consider the number of the cost as 0 only, because after we have put all the words, then basically we will not be having any extra space, irrespective of the fact that whether this was code or anything. Even if 2 word spaces were remaining or anything, will not put any cost here. Okay, so the cost here, if I will see, so the cost comes out to be 9 plus 1, that is nothing but 10 here. Okay, you can see that the cost comes out to be 10 here, right? Now could there be any other way that I could have put it? Yes, suppose they can be various ways, but suppose I'm thinking of one of the other ways. So suppose I have these 6 spaces, so I can do what? I can put the word G and F and G here. Okay, if I put the word GFG here, then after that I take one space. Okay, so after this, what happens? The remaining number of spaces is 2. So can I put go here? Yes. So because I can put go here, so I'll put, let's say, go here. So in this case, the cost of this line will be nothing but 0, because 0 into 0, because I'm not using any extra space is not left in this line. Okay, after that, if I have this, so suppose I put the word CP in this line. Okay, so after that I'll have 1, 2, 3 and 4 spaces, right? Because if I try to put coder here, COD, then ER, then this is not what I have to do. I should put all the words in the same line, right? A single word should be put in the same line. So in that case, I cannot put coder in the same line. So I'll have remaining number of spaces for me to put the word 3, but actually 4 spaces are left, right? Because I was considering one extra space. So that's why I'll say that remaining plus 1 into remaining plus 1 is the number of words, or is the number of spaces wasted in this line. So that will be nothing but 4 into 4, and that will be nothing but 16 here. Okay, after that I'll move to the next line, 1, 2, 3, 4, 5, 6, right? So after that, the next line will have 6 characters, and I'll put the coder word here. Okay, CODER. When I put it, so one space is left, but I'll not consider it, because after putting the last word, I will not consider any extra spaces. So actually the cost will be 0. So 0 plus 16 plus 0 will be nothing but 16. So there can be various ways to put it, but if you will put the word in this particular sequence, in that case the cost for you will come out to be nothing but 10, which is the minimum cost. If you will see here, for this test case, when you are given 3, 2, 2 and 5, you will just be given the length of the words, and you will be given the number of characters that you can put in a particular line, that is k is equal to 6 here. So you can see the cost comes out to be nothing but 10 here. Okay, so what are the various options? Now if I have to think about all the possibilities, right, when I get to know that I have to think about all the possibilities, so which concept comes to my mind, which particular algorithm or technique comes to my mind? Obviously recursion, when I have to think of all possible ways of putting the characters. Okay, and also notice one thing, that I have to put the characters I have to put the words one by one in the sequence in which they are given inside this array also, right? So I have to take care of this thing as well. Okay, now what I can basically do here is, suppose if I have the words, right, if I have a particular word, if I have an ith word, okay, and I have like let's say I'm calling the recursion, okay, in the recursion I have the current index I, okay, I have the index I, that is the current word ith word length of the ith word that I want to put, okay, I have some remaining number of spaces currently passed, I have the array and I have passed k value as well. Okay, so what I can say is, if these things are passed, so there can be two scenarios that can lie in front of me. Okay, there can be two scenarios. The first scenario can be that if the array of I, right, if the size of the ith word is greater than the number of remaining words, right, if it is like, suppose in what happens, suppose I put the word go and then I had 6 spaces, right, so I've put the cp word, like what I've done is, suppose I've put the cp word, right, suppose I've put the cp word. Okay, after that if I want to put the word coder, so I'll take one space and then I'll try to put cod then er, so I cannot put, right, because the number of remaining spaces are what, the number of remaining spaces in which I can put the words is nothing but 3, and the length of the ith word is 5 because coder word is of length 5. In that case I have to move to the next line. Okay, because in this case you can see, in this case I will place this word and I'll move to the ith word, so I'll take this space as extra, right? So in this case the remaining space is nothing but 3. The remaining number of spaces, in which I can put the characters is 3, and then the length of the ith word is what, the length of the word, suppose the word is coder, so the length is actually 5. So in this case I can say that I cannot put it in the same line. So in that case what will I do, I'll try to put it in the next line. If I put it in the next line, so I'll put coder here in the next line. When I put coder in the next line, in that case what will happen, I will simply say that if I put coder in the next line, then these are the remaining spaces that I have left. So you will say that okay, the remaining spaces are 3. No, actually not 3, it is nothing but 4, because I'll take this space as well. Because if I had started to put the word like if I started to put the word starting from this here, then I would have not considered this space. But since I'm not putting any word, so all these spaces are empty after putting the last word in this line. Okay, so in that case I will say that remaining like I'll pay the cost, that is nothing but I'll pay the cost here, and that will be nothing but remaining plus 1 into remaining plus 1. Okay, I'll pay this much cost and then I'll call recursively for I plus 1 the next word. Okay, and the remaining number of words will be what, now if I place the ith word in the next line. Okay, suppose after coder also there were several words, so if I put the coder word, suppose in the next line, okay, in that case in this line I am putting, so initially k number of spaces were remaining and I have taken array of I number of spaces, right? So after that I'll take one more space, suppose there were several spaces here, so k is the number of spaces that were remaining in the next line. Okay, because I'm taking a new fresh line, and then array of I is the length, is the number of characters that I will take, minus 1 as well, because I'll take one space extra and then I'll start putting the words if there were any other words, right? So in that case I'll pass the remaining number of words as nothing but k minus array of I minus 1, and I'll pass array comma k here, right? This is what I will pass. Now other than this, what are the two circumstances? Suppose if the length of the ith word was lesser than equal to the remaining number of spaces, as I mentioned. So if it was like, if suppose that I had put already the gfg word, I had already put there, right? If suppose 6 spaces were there and initially I had put the gfg word here. Okay, after that I had 3 spaces. So basically the remaining number of spaces were 2. And can I put the word, let's say, go here? Yes, I can put the word go here, right? I can put the word go here. So either I can choose to put it in the same line or I can choose to put it in the next line. So either I can put it in the next line like this. I can put go here, and in that case if I put in the new line, then the remaining number of spaces will be k is the freshly, since we are using a fresh line. So like I'll pay first of all a cost. The cost will be nothing but remaining plus 1 into remaining plus 1, as we have discussed in the last case. Then the number of remaining then I'll move to the I plus 1th word, and for that word the number of remaining spaces would be nothing but I'll take this space and then the remaining number of words. So that will be nothing but k minus array of I minus 1, as I already discussed. So if I put it in the next line, okay, if I put the ith word in the next line, because I have a choice either to put it in the same line or not. Okay, so if I put it in the next line, in that case what is going to happen with me is, basically in that case I can say that if I put it in the next line, then I'll pay a cost of remaining plus 1 into remaining plus 1, okay, plus what, plus I will call it recursively, right, plus the recursion of I plus 1 comma k minus array of I, okay, comma array comma k. Okay, that is what I will basically be doing here. Now once this part is done, right, so either I have the choice to put it in the next line or I can put it in the same line. So suppose I put it in the same line. Okay, if I put it in the same line, in that case I'll not be paying any extra cost, right? Suppose the words were like this. Okay, suppose I had 6 places and I had to just put the word CP here, right? And then after that, what I do is, suppose there were several other spaces, and after that I put the word go, like suppose I put the word, let's say there was another word, let's say something like CS. Okay, if I put CS, then after that I'll take one space, and then the remaining number of spaces will be this much, right? So in that case I'll not pay any extra cost, and the remaining number of spaces will be nothing but the spaces that I had initially, that is the remaining spaces minus the length of the current word, and minus 1 also, because I'll be taking one extra space, right? And in this case I'll not pay any extra cost. So these are the two choices that I have, right? So this is how the choice diagram would look like. So I'll quickly make it. So if I'm putting it in the same line, then in that case I'll not pay any extra cost, and I'll return recursion of I plus 1 comma remaining minus array of I minus 1, okay, and comma, I'll pass the array and I'll pass k value as well. Okay, these will be the circumstances, right? So in this, since I have to minimize the cost, so I either have the choice to put it in the next same line or the next line. So I'll take the minimum out of these two, right? I'll take the minimum out of these two. And here, if I have only one choice that I have to put it in the next line, then I'll put it in the next line also, right? And if I have placed all the words, if I've reached the end of the array, if I've placed all the words, then the cost will be zero, and that will be my base case. So I can simply return 0 in that case. Okay. Now the question comes, like, will that be optimal? Will this much recursion be optimal? No. As you know, recursion is always exponential in nature, right? If I ask you to tell me that what is Fibonacci of 6, suppose I tell you that, okay, Fibonacci of 1 is 1, Fibonacci of 2 is 1, and you tell me Fibonacci of 6. So you'll say that Fibonacci of 6 is nothing but Fibonacci of 5, and Fibonacci of 4. Fibonacci of 5 is Fibonacci of 4, and Fibonacci of 2, this is when you are calculating it using recursion, right? Then Fibonacci of 4 is what? Fibonacci of 3 and Fibonacci of 2, correct? Fibonacci of 3 is what? Fibonacci of 2 and Fibonacci of 1, right? Plus Fibonacci of 1. Fibonacci of 3 is what? Fibonacci of 2 plus Fibonacci of 1, and Fibonacci of 4 is what? Fibonacci of 3, Fibonacci of 2, and Fibonacci of 3 is what? Fibonacci of 2, Fibonacci of 1. So in this case, if you will see, are there several recursive calls that are calculated again and again? Yes. If you see, if f of 4 is already calculated, will you calculate it again? No, because in this case the time complexity of the current function will be order of 2 to the power n, right? That's exponential in nature. But you can reduce it to order of n. Why? Because you can, if you have already calculated a certain value, then you will not calculate it again and again, right? So if f of 4 is already calculated, if you have gone down so much, if it was not calculated, then initially it can be marked as -1 if it is not calculated. If dp of 4 is not calculated, if the fourth Fibonacci number is not calculated, you can mark it as -1 in some dp array. And if after that, when you calculate it, then you can then before returning it, you can store it and then return, right? After that, when you come here, when you see that, okay, dp of 4 needs to be calculated, like if Fibonacci of 4 needs to be calculated, that is the fourth Fibonacci number needs to be calculated. In that case, will you calculate it again? No. Will you go down again and calculate it? No. What you will do is, you will simply say that it is, if it is not equal to -1, that means it must have been already calculated, so you'll simply return the value. Okay, same case goes for f of 3 as well. If f of 3 is already calculated, will you calculate it again? No, right? So you can observe, if the larger size is there, then you will not be doing this again and again, because that will be exponential in nature and you will try to bring the complexity down. Similarly, if you are having recursive calls, right? So in this case, you are having, every time you are at most having 2 recursive calls, right? So it might happen that suppose this particular recursive call with a particular, which are the 2 parameters that are changing here? I is changing and the remaining number of words are changing, correct? So if like suppose I is equal to 4 and the remaining number of characters that I have in this line are 4, are 3, okay? And suppose this, in this state also, the I is equal to 3 and the remaining number of words is 3. So I is equal to 4 and remaining number of characters that I have in the line is nothing but 3. So if I have already gone down and calculated it because it was -1, then I'll not calculate it again. If I see this state again, so I'll not calculate it again. I'll simply return the stored answer. So for this, I can take a 2D DP, right? 2D array for initially storing all the states as -1. If it is not already calculated, then I can simply calculate it, store it, and then next time if I want to calculate it again, so I will not calculate it again. I'll simply return the stored value. That is nothing but the concept of memoization, or we can say top-down DP. So let's see what are the dimensions of this particular words. So I can say that the dimension n is equal to 505. So the I can go at most 505. So first dimension I can take as like I can go till 500. So I can take it as 505, and the k value can go till 2000. So I'll take it as 2005. Okay. Now let's try and write the code using DP memoization. So what I'll do is, first of all, I'll declare a DP, and it will be of size 205. Okay, comma 2005. After this, what I will do is I'll initialize all the states as -1. So basically what I will do is I'll use memset. So basically you can run a loop ij and you can initialize as it as -1 in case of Java or any other language. But in C++, I can initialize this DP of this dimension as -1 using the memset. After this, what I will do is I'll simply return what? I'll simply return recursion. I'll start from the 0th index. Initially, what I will pass is, let's say instead of this num, I have the array as arr, okay? So initially the remaining number of words is k, and I'll pass the array as well, and I'll pass the k value as well, okay? After this part is done, so what I'll do is I'll write the recursive function. So int recursion, it will be int I, okay? After int I will have int remaining number of words that I currently have, okay? So I'll pass int remaining, and other than this I'll pass also the vector. So vector int ampersand array is what I will be passing, okay? And I'll also pass the k value, okay? K does not change, so I can pass it with ampersand, right? After this part, if suppose after several recursive calls, if I have exhausted the array, so if I is equal to array dot size, if I've reached the end of the array, in that case if I've placed the last word, so for the last word there will be no cost, right? Because after placing the last word, if even some characters are remaining, so I'll not consider them as the question says that, so I'll return simply 0. Otherwise what I will check is, otherwise I'll check that if the dp of I and the remaining number of words, okay, if it is not equal to -1, in that case what I will do is, if it is already calculated, because if it's not equal to -1, so that means this particular recursive state is already calculated, then I'll not calculate it again, otherwise the time complexity is going to be exponential. So in that case, if it is already calculated, I'll simply calculate it and then I'll simply return it without calculating. Otherwise, if it's not calculated, so I'll declare an answer, okay? And what are the two scenarios in front of me? The two scenarios are that if the length of the ith word is greater than the number of remaining spaces that I have in the current line. In that case, what I can say is, in that case I can simply say that I will be required to move to the next line, so I'll say that answer is equal to nothing but recursion of I plus 1, okay? I'll have to bear the cost as well. So what is the cost that I have to bear? The cost that I have to bear is remaining plus 1, okay, into remaining plus 1, okay? This is the cost that I will have to bear, plus I'll pass the recursion for I plus 1, comma, the remaining number of words will be what? If I'm putting it in a new line, then k were the initial number of spaces that I had left, minus arrow 5, because that much spaces I'm occupying, minus 1, because I'll be taking one space as well, okay? Then I'll pass what? Then I'll pass the array and I'll pass the k value as well, okay? Other than this, if I go to the else, right, if I can place it, if I have a choice either to place it in the same line or the next line, so I'll explore both the choices. So what is the choice one that I have? The choice one that I have is nothing but I can either put it in the next line. So if I put it in the next line, then I can say that remaining plus 1 into remaining plus 1 is the number, like remaining number of spaces were there when I was putting it in the same line. But if I don't put it in the same line, then I was taking one extra space now for distinguish between each word. So that's why remaining plus 1 into remaining plus 1 will be the cost, and then I'll place the ith word in the next line, so I plus 1, and if I, after placing the next one in the new line, so the remaining number of spaces will be k minus rf I minus 1, okay? Then I'll pass the k here, okay? After this part is done, so what I can say is, what will the choice 2 for me? So the choice 2 is that this is when I put it in the next line, when I put the ith word in the next line, okay? Or I, like, say if I put it in the same line, if I put it in the same line, then I'll pass the recursion, I'll call for I plus 1, right? I'll pass I'll place the ith word in the same line. If I'm placing it in the same line, so initially I had the remaining number of words as rem. Then if I'm placing the ith word in the same line, then basically rfi is the number of word spaces that I'm occupying, minus 1. Why minus 1? Because I'll be, for placing the next I plus 1th word, I'll be taking one extra space, right? So for that, the new number of remaining spaces will be remaining minus rfi minus 1. Then I'll pass the array, and what I will pass is, I need to pass the array. Then I'll pass the array, and I will also pass the k value here, okay? And then my answer will be nothing but the minimum of the two choices. So minimum of choice 1 comma the choice 2 is what I will have. And then before returning the answer, I'll say that, okay, dp of I and remaining is equal to nothing but the answer, okay? And then after I've stored it, so I'll simply return this particular calculated answer, right? Why am I doing this? So that I don't have to calculate the same state again and again, okay? Let us try and compile this code to see if there is any error in this code. It works on the samples. Let us try and submit this code as well. Okay, it gives us a runtime error somewhere. Now why does it give us a runtime error? Okay, so if I is equal to array.size, that I am returning it. Have I taken something incorrectly? Okay, I'm getting a runtime error here. So as per the constraints, its n value is 500, okay, and the k value maximum it can go till 2005, okay? So what I will be doing here is, if the I and remaining is not equal to -1, in that case what I will be doing is, if I am placing it in the, like, what I will be doing here is, what I will do is, I'll pass the TP, I'll pass -1. Okay, initially I'll have all the values as -1, indicating that they are not calculated. Okay, and size of DP, and I'll start from the 0th index. The remaining number of spaces initially will be k, and I'll pass the array, and I'll pass the k value as well. Okay, so am I missing something? Is there some runtime error because of that? Suppose that index I is also there, or let's say, so this part is fine, I think. Okay, so what am I missing here? So if I'll see, so if I is equal to the size of the array, right, if I reach the end of the array, so in that case I can simply return a 0. If I remaining is not equal to -1, so I can return this. Otherwise I'll calculate the answer. So if it happens that array of I, okay, if it's greater than remaining number of words, okay, if the current word is greater than the remaining number of characters that I can accommodate in a particular line, in that case the cost will be remaining plus 1 into remaining plus 1, plus I will call the recursive function for I plus 1, and the new remaining number of words will be k minus array of I minus 1. And when I'm putting it as otherwise, what I can say is, if otherwise I have the choices, right? In the else case I have a choice that either I can put it in the same line or not. So what I will do is, I'll put remaining plus 1 into remaining plus 1 plus the recursion of I plus 1, okay, comma k minus array of I minus 1, fine, and then array comma k, and then I'll move to I plus 1 comma remaining minus array of I minus 1 and array comma k, and then I'll take the minimum out of the two choices, correct? Okay, and then I'll store this answer, and then I'll return it. So let's try and compile this again to see what error we are getting here. 2005, this, okay, 505, sorry. Yes, like what mistake I've done here is, I've taken the second array, like it was 505, it was not 205, so I should have taken it as 505. Now it should get compiled. Let's try and compile it. So I was making mistake in terms of size. Okay, now it gets accepted. So in case if you understood this explanation, so make sure to hit the like button and comment down understood as well. Thank you. In this video we will discuss the problem snake and ladder. This problem is very famous and has been asked in various interviews. So the problem says that we have been given a 5x6 snake and ladder board. So basically we are very well aware, we have played this snake and ladder game in our childhood. Okay, so it says that we have been given what? We have been given a 5x6 snake and ladder board, and we have to find the minimum number of dice throws which are required to reach the destination or the last cell 30. Okay, so since this is a 5x6 board, so what we need to do is, like, we have to start from the cell 1 and we want to reach the cell with the value as 30, that is the last cell of this particular grid. So we have to tell that what is the minimum number of moves or the minimum number of steps in which we will be able to reach the last cell. It says that you are given an integer array n which denotes the number of like the total number of snakes and the ladders. Okay, so basically if you will see, so there are some places, like in this diagram, if you will observe, let us just quickly copy this diagram. Now let's see this diagram here. So if you will observe this particular diagram, so here one thing that you can observe is at 3, we can observe that at the position 3 we have a ladder. So when we reach 3, so actually we will not stay at 3 but we will reach 22. Okay, so that is indicated by the array with pair 3 32, right? 3 along with 3 adjacent to 3 you have 22. So when you have 22 adjacent to 3, so that means that if you are at 3, then you will actually take up a ladder inside the array. If you have this information, then that means if you reach 3, so actually you will directly reach 22. Why? Because you will go up, right? And the information in this array also is given like this, right? If this is there, like if this is there, so they will give you 3 comma 22, right? After that, like every information will be given this in this array in form of pairs indirectly, I and I plus 1 pair starting from I is equal to 0, even indexes, right? Then if I see here, so I can observe this part that if I start from 5, if I reach 5 somehow, then I will actually not reach 5 but actually I'll reach 8. Okay, you can see that I'll reach 8 actually, right? So if I'm at 5, so 5 comma 8 pair will also be given in the array. If I see another pair here, let's say I am at 11, so 11 and 26 pair, right? 11 comma 26 will also be given in the array. All the information will be given in a single dimension array like this. Okay. Then if we will observe further, so if we go further up here, so we can observe that is there any other snake? Yes. We can see that at 17 you have a snake. Okay. So since at 17 you have a snake, and if you get a snake at 17, then you will reach 4, the cell 4. So you can write 17 comma 4 here as well. After that, if you will observe, so we move to, like, after that we move to 18, then we see then 19. So if we were at 19, then we will reach 7 actually, right? After this, if we see 20, so if we would have reached 20, then we would have reached 29. So all this information will be given in form of the array. Let's say we had to reach the cell 27. So in that case, it will make us fall at the 1, right? So this information will be given in form of an array. So you can basically say that if we are given an array, so for all the even indexes starting from 0, 1, 2, you can see 0, 1, 2, 3. So all the even indexes like I is equal to 0 has a pair with 22, right? If you are at 3, if you are at the cell 3, then you will reach 22. If you are at the cell 5, then you will reach 8. Okay. So for every I, you have a I plus 1 pair. That tells you for many of the indexes, you have been given this array. That is the combination of snake and ladder. Okay. It is not necessary that for every cell like it will be given, because for 24 you can see neither there is a snake there nor there is a ladder. Okay. So this 24 will not have not be mentioned in the array, but like many of the informations will be mentioned in the array. So basically it says that I will have an I plus 1. Okay. Every I and I plus 1, like you can say that it will, the size of the array will be 2 cross n. So you can start from I starts from 0, I is lesser than 2 cross n. Okay. Then you can skip every second value, and you can say that every array of I has a pair with array of I plus 1, right? So I need to store it somewhere, right? I need to store some this kind of relationship. So if I want to store this kind of connectivity in the that is given in the array, so what I can think of first of all doing is I can say that I will start from 0, okay, because 0, like I is equal to 0 and I is equal to 1 have a pair, right? Then I is equal to 2 and I is equal to 3 have a pair, right? So basically according to the index of the arrays, right, the values will be there. So array of I and array of I plus 1 have a pair, so 2 cross n pairs will be there. Then I plus is equal to 2, because I'll skip every 2th, like every 2th index I is equal to 0 is having a pair with I is equal to 1, then I is equal to 2 having a pair with I is equal to 3, right? So every I has a pair with I plus 1. So that's why I'm skipping 2 indexes. I can make a connection array. Initially, I can mark the connection of everybody as -1. So let's say if I talk about connection of 24. So connection of 24 will be -1. Why? Because 24 is not connected to anybody, if you will observe. Or let's say if I talk about connection of 25. So 25's connection will still be -1 only, because if you go to 25, then you will not go anywhere else. Neither you will go down the snake or now you will go up the ladder. Okay, because there is neither a snake present at that index nor a ladder present. Okay, so what I will be doing is I'll say that, okay, connection of RFI is equal to RFI plus 1, right? This is the first thing that we need to observe in this particular problem. After we have observed this thing, so what are the further conditions? It says that we have to find this in minimum number of moves. So suppose that currently we are at a current cell, right? Suppose that we are at a current cell. We are at a particular current cell. Okay. So what can we do? Where can we go? We can take either a jump of 1 and reach current plus 1, correct? We can take a jump of 2, reach current plus 2, correct? Like this we can move. Like we can, since this is a dice of 6 side, we can move till 6, right? Wherever we are standing currently, we can either move to current plus 1, current plus 2, current plus 3, and so on. Okay. And after this, after we move to them, then from after we move to them, so we'll count it as one step, right? Every time when we move, so we'll count all this as one step, right? So suppose, okay, if I had this grid, so what will be the minimum moves that I will be taking in this case? So if I'll observe, suppose that I start from 1. So initially when I'm starting from 1, then actually the number of moves will be 0, correct? And which since you can see this is a graph, and if I have to traverse it, says that I can reach the destination in minimum number of moves. So which algorithm comes to our mind? Yes, the algorithm that comes to our mind is nothing but the breadth first search. We can simply apply a breadth first search here to find the minimum time in which we can reach the destination, that is 30. And if it is not possible to reach the destination 30, why it will not be possible? Suppose that maybe one of the cases can be that 29, 28, 27, all these last values, last 6, 7 values are filled with snakes. So if it is filled with snake, then it will be impossible for us to reach the last value. So if it is impossible, then we need to return a -1 as well. Okay, so what can we try to do? So initially we can say that the number of steps that will be taken will be 0, and we can, since we are trying to use BFS, so what we can do is we can make a queue for ourselves. Okay, so we will initially insert what? We'll initially insert 1 inside the queue. Okay, this will take 0 number of steps. Then after that, from 1 we can go to 2, or we can go to 3, or we can go to 4, or we can go to 5, or we can go to 6, or we can go to 7, because 7 like 6 different types of jumps we can take, right? And all these jumps will take nothing but 1 step, right? This will be the first step, right? This will be the first step. The steps will be nothing but 1. Either in 1 step I can reach to 3, or either in 1 step I can reach to 6, right? So that's why they will be storing 1 step only, right? So this is one thing that I need to see, that I'll be doing a level order traversal. Like I'll be incrementing the step level wise only, right? I'll first of all take the size of the current level. So currently there will be 1 only. So after 1 is processed, so after that I'll do a step plus plus, and after that all these nodes I'll process inside a while loop without incrementing the steps, because they all can be reached in just the first step itself, right? After that, from 2, where can I reach? So if I was at 2, then from 2 I can go to where? I can say that if I'm at 2, so either I can go to 3, or I can go to, like, from 3, like from 2, either I can take a jump of 1, or I can take a jump of 2, either I can take a jump of 3, or either I can take a jump of 4, either I can take a jump of 5, either I can take a jump of 6. Now I can see that why this problem seems to be a little bit inspired from the DP concept, although you will not be applying directly DP, but you can see that we already have 3 here, right? If we already have 3 here, so if you have already a state present that is visited, so will you calculate it again? Will you calculate this again? No, because 3 here you are reaching in 3 steps, but here you reached like in the second step you are reaching 3, but here you reach 3 in the first step itself. So if you have visited a particular cell already, then you will not be visiting it again. That is also one more important thing that we need to observe here, right? So we will say that we will keep a visited array with ourselves, and if we have visited a particular cell, if we have already computed the minimum number of steps for a particular cell, then we will not compute it again. So that is why the DP tag is there in this problem, right? Okay, so what we will be doing here is, we will simply say that, okay, if this kind of a scenario is there, then after that from 2 I cannot reach 3, I cannot reach 4, then I cannot reach 5, because they are already there, 6, 7, then I can reach 8 maybe. So I'll insert 8 into the queue. The number of steps taken will be 2 here, right? After that I'll see 3, so from 3 either I can reach 4, 5, 6, 7, but all of them are visited, so I'll insert 8 is also visited, so I'll insert 9 and things like that. Okay, then after that, suppose what happens when I, like, after that, suppose I reach 3. Okay, so I will reach 3 in which, how many number of steps? Like I will reach 3 in 1 step, correct? I'll be able to reach the node like this 3 in 1 step, because from 1 I can take a jump of 1, like I can take a jump of 2, and I can reach 3. The moment I reach 3, so actually I'll not be at 3. Okay, I'll not be at 3. I'll need to check the connection error, right? If for a particular current ith cell that I'm at, right, ith cell that I've reached, if the connection of I is equal to -1, right? So in that case I will say that inside the queue I can simply push I, because if I reach 2, then from 2 I cannot go anywhere, because the connection of I will be -1 itself. But from 3 actually I can reach, like actually I'll take a ladder from here, right? So this thing I've already stored in the connection array that I've taken. So from 3 I will be reaching 22. So else, if it is not -1, then I'll simply push what? I'll simply push the connection of I, like whatever is present in the connection array, because from 3, for 3 I have the connection is nothing but 22. For 3 I'll actually be reaching 22, so that's why I need to store it. So let's see how many steps we will take. So if we start, so for reaching 3 we will take 1 step, then for reaching let's say 22, okay, so for reaching 3 we will take, let's say, 1 step, then for reaching, let's say, 22, from 3 we'll reach 22, and we'll not take any step further, right? After that, let's say what we can do is, we can take, like, up till now how many steps we have taken. Like we directly reached from 1, we jumped to 2, 3, and then we reached this 22, right? This took 1 step. Then in the next step what I can do is, maybe I can reach 26 in the second step, right? After that I can take a jump till here, so from 22 I can reach 26 in 4 steps. Then after that I can take another jump and I can reach 30 directly. So you can see that in 3 steps I was able to reach, correct? So this is how we will be doing. And if we have already calculated a particular state, so we'll not be calculating it again. That is why we are using the concept of visited array, and that is where the DP intuition a little bit kind of this thing comes, that if you have already calculated, If you've already visited a particular cell, then you will not be visiting it again. Now let us quickly try and write the code for this approach. So what we will be doing here is we'll be given the n and the m. Okay, so we'll be given the n and the n, and what we will be doing is we will declare a vector. First of all, int the connection array that we have proposed. So it will, like, the total number of 30 cells will be there. So first of all, we'll initialize it as -1. Then what we will be doing here is we will iterate. So for int, we can say that like our int I will start from 0. I will be lesser than 2 into n. Then we can do I plus is equal to 2. Okay. After this part is done, so we will simply say that what we need to do is we need to say that for the connection of RFI, RFI is actually connected with RFI plus 1. Either it will be a ladder or a snake, correct? If RFI is greater than RFI plus 1, in that case we are going to a snake. Otherwise, if RFI is equal, like if its RFI is lesser than RFI plus 1, that means the connection is going towards a ladder, correct? And then what we can do is we can mark the steps as 0, and after this what we will be doing is we'll simply push the node 1 into the queue. Like the starting part will push into the queue. We have marked the steps as 1. So first of all, before that we need to declare the queue as well. So we will declare queue of int queue. All right, and then we also need a visited array. So we will do what, we'll have a visited array. So we can write it as vector int visited for all the 31 states, and initially we can mark it all of them as 0, right? So we have marked the visited as 0, and then we'll mark the visited of 1 as 1 because it is now visited. Then I'll simply start my BFS traversal. So while the queue is not empty, till then we'll keep on iterating. And what we will be trying to do is we'll first of all try to find the size, that is the number of nodes at the current level. So that will be nothing but queue dot size. Okay, and for all these nodes I'll not be incrementing the steps because the steps for them will be the same. Okay, so what I will do here is I'll say that while the size while the size is greater than 0, till then we'll keep on iterating, and I'll take out the current node. So current node will be nothing but the q dot front. Once I take it out, so I'll pop out the current. Okay, once I've popped out the current node, so I'll check that if the current node that I have reached, if it's equal to 30, right? If it's equal to 30, so it's the last node. So I have reached there, so I'll simply return the number of steps, right? I'll simply return the number of steps that I have taken up till now, because if I reach there, then that means the steps must have been updated by now. Okay, other than this, if that is not so, so in that case, if the current cell that I have reached, if it is not the ending cell, so in that case I'll try to go in all the 6, I'll try to take all the 6 jumps from here. So I can say that I can either move to current plus 1 till current plus 6. So I can basically run a loop till there. I starts from 1, I starts from current plus 1, and I is lesser than equal to current plus 6, and I can do an I plus plus here. And what we will try to do is we'll try to see that if I is greater than 30. Why I is greater than 30? Because suppose if you are at 29, okay, if let's say you were at 28, okay, so from 28, if you or let's suppose that you were at a particular cell, right? Suppose you were at a cell like let's say 29, and if you take a jump of 1, then you will reach 30. So you will store it inside the queue. Okay, but if you take another jump, so you will reach 31, or maybe you can reach 32 if you take a jump of 3. If you take a jump of 4, then you can reach 33, right? So in that case you will be out of bound. So if you are out of bound, then you can simply break the loop here. Otherwise it will keep on storing, and the queue will not get empty, right? So if I is greater than 30, then you will break. Otherwise, what we will be doing is we will simply say that if the visited, right, if the visited of I is equal to 1, if the current ith cell is already visited, then we will simply continue from there, right? Otherwise, if it is not visited, then we will mark it as visited because currently we are visiting it. Okay, once we mark it as visited, so we will check that if the connection of the ith cell, if it's equal to -1, right? If it's -1, so if it is -1, so this will simply indicate, if it's -1, then this will simply indicate what? This will simply indicate that at the current ith cell, neither I have a ladder nor a snake. So in that case, I can say that I'll simply push I into the queue. Otherwise, if the current cell is not equal to -1, if the connection of current cell I is not equal to -1, so that means either we have a ladder or we have a snake there. So in that case, we will push the connection of I, because the connection of I, remember for RFI, connection of RFI, we had stored RFI plus 1, right? So wherever we were moving from there, right? So once we have done these things, so what we'll be doing is after we have stored this, So after the while loop for the size is over, then we can increase the number of steps, because that is when the steps can increase. And after this part is done, so after we come out, suppose we come out of the while loop without returning the number of steps, so that means that we will never be able to reach the end. In that case, we can simply return a -1 there, right? Let's try and compile the code to see if it's working. Okay, so a little bit compilation error is there, so q.front. Let's try and compile this now. Okay, so our output is not getting updated, so why is that so? While size minus, I've taken the steps as well, so we are returning the number of steps as well, and our output for the sample is coming out to be 0, whereas it should have come out this thing. Okay, so I think we are making some mistake somewhere, so let's check that out. So we first of all mark the connections as -1, then our I starts from 0 and I is lesser than 2 cross n, then connection of array phi is equal to array phi plus 1. We initially mark the steps as 0, and what we do is we mark visited of 1 as 1, so we mark 1 as visited, we push 1 into the queue, we take a visited array, initially we mark it as 0 and we mark the visited of 1 as 1 as well. After that we iterate, and the size q dot size we run, while the we take out the current, we pop it out. If the current equal to, okay, so I was missing equal, that's why it was not getting correct. Now let's try and compile this. It works on the samples. We are getting 3 steps. Now let's try and submit it for other test cases. So you can see that our solution was able to pass all the test cases. Now talking about the time complexity for this code. So the time complexity of our code will be nothing but order of n, because we are iterating through each and every cell present in the game exactly once, and the space complexity will also be order of n. Why? Because we are using a visited array as well as a connection array. So in case if you understood this problem, so make sure to hit the like button and comment down understood as well. Thank you.